Here's an example of how we can use the convolution theorem to prove a different theorem. So the shift theorem we stated earlier, one of the shift theorems looks like this. So we can prove this to be true using the convolution theorem as follows. So the Fourier transform of the product of these two functions is equal to the convolution of the Fourier transform of the two functions with a factor of 1 and 2 pi at the front. The Fourier transform of f of x we can call f of k. The Fourier transform of e to the I k naught x is a delta function, delta k minus k naught. And the convolution between these two functions is given by this here, where now I've got the dummy variable kappa. Now, we can use the property, the shifting property of the delta function to realize that this convolution is actually just the Fourier transform of k minus k naught, which is what we set out to prove. We've also discovered that the convolution of f of k with delta k minus k naught gives f of k minus k naught. So the shifting property of the delta function with the convolution also has a really useful sort of outcome here. Or expressed in time coordinates, we can write that the convolution of some function of time with some delta function t minus t naught is f of t minus t naught. Another example where we can use convolutions is to make things more real world. So we said previously that the transform of the cosine wave is a pair of delta spikes. Or in other words, we have some cosine wave, and here we have a pair of delta spikes, both in the real axis. Now, there's something wrong with this picture, and that is that here we've truncated the cosine wave. So this is only true really if this cosine wave is infinitely long, but in this picture at least we've only got about 12 cycles, and in any real physical situation you're unlikely to have a cosine wave that is infinitely long because, well, you haven't got that much time. So what we really have is something like this. This function here is really a top hat multiplied by a cosine wave. It's a truncated cosine. So the top hat function truncates the cosine wave. What does this real world thing, this real world function here, actually look like in the Fourier domain? So let's use this function here, the top hat multiplied by the cosine, to calculate what the Fourier transform really looks like. So here's our function. In this example, I've used a as 4 pi and omega naught is 2 pi. And the Fourier transform of this function here is now going to be, in the Fourier domain, a sinc function, which is the Fourier transform of the top hat, convolved with a pair of delta spikes. And we know the convolution with the delta spikes gives us a sinc function offset by plus omega naught and minus omega naught here. Otherwise, we have two sinc functions centered around plus and minus omega naught with some width given by this a on 2. So in other words, the Fourier transform looks like this. Rather than having a pair of perfect delta spikes at plus and minus omega naught, we've got these spiky functions with lots of ripples next to them. So these two sinc functions centered about plus and minus omega naught. And the peak amplitude here of this Fourier transform is at the frequencies plus and minus omega naught, as you would expect for these delta spikes. But there are a lot of other frequencies as well that come about due to this truncation. What if we had a different sort of finite signal? Instead of truncating our cosine function with a top hat function, what if we truncated it with a Gaussian? So we have a function that looks like this. Well, we can do the same sort of calculation. The Fourier transform now will be the convolution of the transform of the Gaussian, which is a Gaussian, convolved with the Fourier transform of the cosine, which is a pair of delta spikes. So now what we have is a pair of Gaussians offset by plus and minus omega naught, and that gives us a Fourier transform that looks like this, two Gaussian spikes. Now we are lacking these ripples on either side. These ripples were coming from the sinc function. The Gaussian truncation gets rid of those ripples. It's a much cleaner sort of truncation. So we get two Gaussians centered about plus minus omega naught, and the smooth Gaussian truncation gives us fewer frequencies than that messy sinc function due to the top hat truncation. Here are a final few properties of convolution. Convolution is commutative, so that the convolution of f with g is the same as the convolution of g with f. The convolution is associative, so if you have a convolution written out like this, where you're convolving f with the convolution of g and h, then you can move the brackets around freely. Convolution is distributive, so you have a sum of two functions here and you find the convolution with the sum, then you can take the convolution with these two things separately. And so these are useful properties to bear in mind when you're manipulating convolutions.